So this is we're going to start with transition metals. The first thing that we're going to do is okay, we're going to try and figure out uh, what are transition metals. Okay, and you have this. Usually, what you see is you see this this box over here, this middle box over here. A lot of times people call this transition metals, but not all of them are transition metals. Most of the metals in this box are transition metals. Technically, these are called d block elements. Okay, why are they called d block elements? Because the last electron in you call them d block elements because if you write the electronic configuration, the last electron always is filled in a d. So it goes into d subshell. So you can pick any element, and we're going to focus on these elements over here, the top row. Okay, that is what we're going to focus on. Most of the elements in the top row over here. So it's scandium, titanium, vanadium, etc., chromium, manganese, and we're going to try and write the electronic configuration of a few of the elements. So starting with the scandium, remember these are d block elements. 21 electrons, so it's going to be 1s2 and 2s2, and then you have 2p6, 3s2, then 3p6, and then you have 4s gets filled first, and then the 3d would have one electron. Now all of them are going to have, all transition metals are going to have exactly the same electronic configuration up till this point. I mean, this is 18 electrons. So what you could do is you could write this as argon, followed by 3d1 and 4s 2. And the rest of them are going to have exactly the same electronic configurations. It's not going to be different. I mean, after scandium, it's what is the element that you have titanium. So titanium over here is going to have exactly the same electronic configuration. So if I write the electronic configuration of titanium, then that is going to be 22 electrons. Nothing would change except for the fact, let me pick this up and so nothing would change. It's going to be the same argon 18 electrons, and then you're going to have 4s gets 2 electrons, and then there would be 2 electrons in the D. So every time every transition metal in a particular row has the same shell numbers and the same subshells. The number of electrons are different. So you have if I pick iron, iron is 26. So the electronic configuration is exactly the same. It's argon followed by 3d 4s 2 electrons and then 6 electrons in the D. Remember that there are two special cases in electronic configurations when you're writing electronic configurations of transition metals. So the two special cases whose electronic configuration is going to be slightly different. One of them is chromium. So chromium has 24 electrons. 24 electrons means it's going to be argon, 18 electrons, and then it's supposed to be 4s2 and 3d4. I mean, technically, this should have been the electronic configuration based on the way we write electronic configurations, but instead, the half-filled electronic configuration is more stable. So instead, you have 5 electrons over here, and you have 1 electron over here. So then there is another special case, which is copper. Now, copper is 29 electrons. So that means it's argon, and it should have been 3d and 4s, should have been 4s2 and 3d9, but instead it is 10 electrons over here, and there's 1 electron in the 4s. So in these two specific cases, half-filled and completely filled arrangements are more stable. Half-filled or completely filled, these subshells are more stable. Okay, so this is chromium and copper. So now I'm again insisting that all transition metals, they have exactly the same electronic configuration. Is 3d and 4s, 3d and 4s. Every one of them has the same electronic configuration. Uh, all D block elements. Okay, so they have the same number of exact same number of subshells. Now we're going to discuss five properties of transition metals that we studied in O levels. So I'm going to list transition metal
Alright.
properties. Number one, kya tha, कि it was they had high melting and boiling points. Okay, that was number one. Compared to other metals, their melting and boiling points are significantly higher. Number two was that they had high densities as well. They were very heavy. For example, gold is very heavy. Similarly, lead is extremely heavy. So they had high density as well. Number three was that uh, they formed colored compounds. Then there was another one which was number four. You had that they had variable oxidation states or variable charges. So, for example, iron is 2 plus. Iron could also be 3 plus. And then you had number five, which is that they were good catalysts as well. So these were five very important properties of transition metals, um, which is why they were called. Uh, and based on these properties, you would identify a transition metal. I'll just give you some examples of good catalysts as well. That iron was used as a catalyst in the Haber process. Then there was vanadium pentoxide V2O5 that was used as a catalyst in the contact process. Then you had another one which is nickel. It was used in hydrogenation of alkenes or hydrogenation of unsaturated vegetable oils. So there were three common catalysts that you studied in O levels, even in AS as well. I said now in A2, what you have to do is we have to discuss each property and why do they have this property in the first place? Why do they have high melting and boiling points? Why do they have high density? Why do they have colored compounds and variable oxidation states? And why this has good catalyst? So we're going to study the same properties but in a lot more detail. So starting with the first thing, so what is a transition metal? That's the first thing that we have to discuss. Now, transition metal by definition, and you must know this definition. Remember, I showed you D block elements, and I told you not all of them are transition metals. They have to. Transition metals are those metals that follow these properties that we discussed. These five properties. If they're not following those five properties, then they're not classified as transition metals. Now, one way to figure out whether it's a transition metal or not, that way is that the definition is that transition metals are atoms, are D block atoms or D block elements that are going to form stable ions with incomplete d subshell. So the definition is based according to the ion that they form. It's not the atom that's important, it's that do they form a stable ion and does that stable ion have incomplete d subshell. So the d subshell must not be full, it must not be empty, it has to be incompletely filled. So for example, you have iron over here. Now Fe is a transition metal, it has 26 electrons, normal atom. The electronic configuration of Fe is argon, and then it's 3d6 and 4s2. Now Fe is usually forms 2 plus. That's a stable ion. So 2 electrons are gone from the 4s outermost. So is the d subshell incomplete? It is. So that means Fe or Fe2 plus is going to behave as a transition metal. Similarly, if you look at other elements as well, for example, if I take chromium for instance, chromium can form 2 plus as well. Now, chromium had 24 electrons. It was argon, and followed by it had 3d 5 and 4s1. Now, 24 indicates and 2 plus indicates that this is gone, and 1 electron from this side is also gone. So this D is going to be incomplete. It is incompletely filled. So both of them behave as transition metals. Then there are certain D block elements which are not going to behave as transition metals. For example, you have scandium. Scandium is 21 electrons. The electronic configuration of scandium is argon, followed by its 3d1 and 4s2. Now, the stable ion that's formed by scandium is 3 plus. Now, if it's 3 plus, then the electrons that would be lost would be from the 4s and also from the 3d. So it's not going to have a 3d subshell. So it's not a transition element or a metal. Similarly, there's another substance which is not a transition metal, and that is zinc. Zinc has a total of 30 electrons. It's also in the same group. Right? If you look at the group over here, there's scandium right at the start, and there's zinc right at the end. Okay, these two, I'm going to cut them out over here as well. Okay, these two are not. So these two are not transition metals. Okay, so this is the top row. The first and the last one are not transition metals. So why is zinc not a transition metal? That if you look at normal zinc is going to have an electronic configuration of argon, followed by it's going to be 3d10 and 4s2. But if you look at zinc ion, zinc forms a 2 plus ion. That's the stable ion. Electrons would be lost from the 4s. The D is not incompletely filled. It is completely full. So again, by definition, this is not a transition metal. So then you have certain substances which at times behave as transition metals and at times they don't behave as transition metals. For example, you have copper. Now, copper has a total of 30 electrons, so its electronic configuration is argon, followed by its not 30 electrons, copper has 29 electrons. So its electronic configuration is the 3d is 10 and 4s is 1. Now, if copper forms 2 plus ion, electron would be lost over here and one would be lost over here, then it's going to be a transition metal. It's going to behave as a transition metal. Why? Because the D subshell is incompletely filled. But sometimes copper 1 plus is formed. So copper 1 plus is going to have argon and 3d would be 10, 4s would be 1, electron would be lost from 4s. Now copper 1 plus um, is not going to behave as a transition metal. So copper would display the properties. We listed 5 properties. It would display those 5 properties if it's forming a 2 plus ion, and it would display those 5 properties, or not all of them, if it's forming a 1 plus ion. And so why is it important that the D subshell has to be incompletely filled? I'll just give you a hint at the beginning. We're going to discuss this in detail later. So incomplete D subshell leads to the formation of colored compounds. Okay, we're going to discuss this in detail a lot later. So any compound that has either a full D subshell or or an empty d subshell, it's not going to be capable of forming correct compounds. So incomplete d subshell is very important. That a transition metal has incomplete d subshell. Its ion has incomplete d subshell. So if this is clear, we're going to move to the next property and we're going to discuss. We're done with the definition. Okay, which elements are transition metals and which elements are not going to behave as transition metals. Now we're going to discuss each property individually. The first one that we're going to discuss is your high melting and boiling points. So we're going to discuss that in detail. Okay, why do they have high melting and boiling points? Now they're all metals. So transition metals are metals. The obvious reason they have high melting and boiling points is that they have strong metallic bonding. Because if the metallic bonding is very strong, then obviously it would be very hard uh, for it for it to melt or to boil. So now the question is, why do they have strong metallic bonds? So we're going to start with the first thing, with the basics, and that is, okay, what's a metallic bond? Now, metallic bonding in O levels, you studied that you're going to have lots of positive ions. So here are my positive ions, positive metal ions. TK metals, they like to lose electrons. They always form positive ions. So they all form positive ions. And the electrons that are lost, they are just roaming around in the middle. TK, so you have these delocalized or free moving electrons that are roaming around in the structure. So metallic lattice is that they form a giant metallic lattice. This is known as a giant metallic lattice. Lattice simply means a regular arrangement of ions where you have positive metal ions. They are present in a sea of free moving electrons. So they are present in a sea of free moving electrons. So this is metallic bonding. Now the first thing is, what is the force of attraction in a metallic bond? Why is this structure? Why is this lattice together? Why and what is the force that's keeping them together? So the force of attraction is between your delocalized electrons. So you have a bunch of delocalized electrons, and they are your negatively charged particles. And you have your positive metal ions. They're obviously positively charged, so they're both mutually attracting each other. So they attract each other, and there's going to be a force of attraction between them. So if I increase the size, what's basically happening is that the electron right in the center, for example, if you look at this electron over here, the one that I'm marking, this electron is going to attract, and it's going to attract the positive ions from all sides. This positive ion, it's going to attract this positive ion. All these positive ions are going to get attracted to this single electron. And when these positive ions they get attracted to, so this electron is basically acting as a glue. It's keeping all the positive ions held together by its attractive force. This other electron is going to do the same. So in the gaps, all these electrons, delocalized free moving electrons, are present in the gaps, and they're attracting all the positive ions together. So they're acting as a glue. So because of the free moving electrons, there's some properties that a metal has. For example, this one, free moving electrons. They're very good conductors of electricity. Then there are certain other properties like the metal ions are not rigidly or tightly held together. So they are malleable and ductile as well. Positive ions can slip and slide when a force is applied. When a force is applied. Anyways, we're not here to discuss metallic bonding. I just gave you a brief idea of what metallic bonding is, and how is the structure strongly held together. So now the issue is, why do transition metals have stronger metallic bonds? Their structure is going to be identical as well, but why do they have stronger metallic bonds? Uh, the reason they have stronger metallic bonds is, uh, and there are two reasons. Let's focus on these two. Okay, what does the metallic lattice depend on? If there are more delocalized electrons, you can imagine there's more glue in the structure. Like if you have more electrons over here, instead of having one electron over here, like this one, which I'm marking, let's say you have a few more electrons over here, then obviously the positive ions would be even more attracted to these electrons, and the force of attraction would have been much stronger. So transition metal have more delocalized electrons, but why do they have more delocalized electrons? That's an issue. So that's one thing. Transition metal have more delocalized electrons in the lattice. In the metallic lattice. So the question is, why do they have more delocalized electrons? And the answer is, like if I compare calcium, let's pick calcium. Calcium has 20 electrons, so it's argon. Then it's the 4s is 2 and the 3d is 0. Now, calcium usually loses just 2 electrons. Why does it lose 2 electrons? Because these are the outermost 2 electrons, easy to lose. Okay? I mean, this electron over here, or these electrons over here, they're very far away. So it's very easy for calcium to lose these electrons, because the next electrons are somewhere really close to the nucleus. So it's going to be very hard for calcium to lose those electrons. Achha, but then if you pick and calcium has how many protons? Calcium has a total of 20 protons. But when you reach iron, now iron in the same row, you have iron. Iron has 26 protons. So it's again argon, and it is 3d6 and 4s2. Now the issue with these two orbitals is that 3d and 4s almost have the same energy levels, which means that they are almost the same distance away from the nucleus. So they almost have the same energy levels. So the question is, if electrons can be lost from the 4s, they can also be lost from the 3d. I mean, not a lot of energy would be required. Calcium के case में there was an issue that if you lose electrons from 4s, losing more electrons required that you went very close to the nucleus to lose some extra electrons, which was impossible because the nucleus was holding those electrons very, very strongly to itself. But in the case of iron, electrons are lost from the 4s, but they can also be lost from the d subshell. So this d subshell is very far from the nucleus, and this is also available for losing electrons. So if you look at the data booklet and you look at the ionization energies, you would notice find calcium. Calcium is over here. Look at the first, removing the first electron, that's easy. 590. Removing the next electron, that's also from 4s, that's easy. फिर एकदम से it becomes 5,000. That's like 5 times the energy is required to remove the third electron, because it's very close to the nucleus. एकदम से you have to go very close to the nucleus to remove the third electron. But let's pick iron over here. Hopefully iron is over here. You would notice that the jump in ionization energies is gradual. Like Fe, losing the first electron, that is relatively easy. Losing the second electron, not much. I mean, the jump is not that big. Iron can also lose the third electron. Now, if iron is losing the third electron, where is it losing the third electron from? Like if you look over here, the third electron would be lost from the inner d subshell. So Fe could also form 3 plus. But the problem comes when it kind of becomes harder and harder for Fe to lose more electrons. Losing the next one, the jump is not that big, but losing the fourth electron kind of it becomes more difficult for Fe. I say even look at the at any other transition metal. The jump in ionization energies is always gradual. It's not a sudden jump. It's not all of a sudden there's a 5 times increase in ionization energies. It's always a gradual increase in ionization energies, which is why they can also have variable oxidation states, and which is why they can also contribute more electrons to the metallic lattice. So if you have a transition metal over here, the number of electrons in the lattice are going to be greater. So the lattice is going to have a lot more electrons, which would be delocalized because of the inner d subshell. There are more electrons available for delocalization. So I'm going to complete what I was writing, which was that 3D and 4s almost have the same energy levels. So electrons from d subshells also get delocalized. And overall, your lattice has a lot more electrons. Now we can also talk about variable oxidation states in the same reasoning. Same reason why transition metals have variable oxidation states. They have variable oxidation states. Why? Because no sudden jump in ionization energies when electrons are removed. So when electrons are removed from 4s or 3d subshell. Okay, so you don't get these drastic increase in ionization energies because the 3d and 4s are almost similar orbitals. They almost have the same energy level. So, anyways, that's the first factor. Okay, why are metallic bonds stronger? Why do they have high melting and boiling points? Transition metals have more delocalized electrons in the structure. Then the other part as well, and that is about the positive metal ion. Transition metals also have greater charge density. Their charge density is greater. And why is it greater? Have greater charge density. So now the reason why it's greater is that look at calcium. Calcium has 20 protons. The electronic configuration, all of them have exactly the same electronic configuration. It's 3d04s2. As you move to the right of the periodic table, what happens? When you move to the right of the periodic table, what happens is the number of protons increase. For example, iron lying to the right of the periodic table has 26 protons, and the electronic configuration is exactly the same. It's 3d6 and 4s2. It's the same subshells. Now, when you move to the right, or when you're traveling to the right of the periodic table, and you come across transition metals, the protons keep on increasing. The protons constantly increase, which is why what happens? More attraction for outer electrons. So there's more attraction for outer subshells. So one thing that happens is that the size of the atom or the ion decreases. It decreases. So for example, you have 20 protons like in calcium, and it's attracting the outer 4s electrons. Now 20 protons are not going to attract those electrons very strongly. So the outer electrons, the 4s and the 3d, are not going to be attracted very strongly. But in the case of iron, the size of the atom is going to be slightly smaller because now you have 26 protons. 26 protons will attract the outer electrons very, very strongly. So all the electrons, they will get attracted. And because the electronic configuration is exactly identical, you can see over here, the outer shell is exactly the same. So the size of the atom or the ion decreases, and it's a smaller size. So if the size is smaller, there's going to be greater charge density. The charge is going to be more concentrated. So for example, you have calcium, which is 2 plus, and you have iron, which is 2 plus. Now the 2 plus in iron is going to be more effective. Why? Because it's a smaller ion, so the charge is more concentrated. So greater charge density in transition metals. So if you're comparing iron with calcium, so Fe with calcium, then this 2 plus on iron is going to be a lot more effective, and it's going to pull other things, negative things, strongly. So that's the other reason. Why is the metallic lattice stronger? Because the positive ion charge density is also greater. So I'll just sum up everything. Okay, why are transition metals having high melting and boiling points? Because simply they have strong metallic bonds. This is a metallic bond, a typical metallic bond, positive ions and sea of free moving electrons. So how do you increase the strength of a metallic bond? The delocalized electrons, you can either increase the amount of delocalized electrons. So I said that transition metals have more delocalized electrons because the 3d and 4s, they almost have similar energy levels. And the other factor was that the positive metal ion that the transition metal forms is has greater charge density because transition metals are smaller in size. If they are smaller in size, the charge is going to be more concentrated. The particles are going to be closer together, and they're going to attract each other strongly. Okay. So this explains everything related to high melting and boiling points.